Hi friends, welcome to the next session of Subject Engineering Mathematics. Now in this session, we discuss classroom workbook on the concept eigenvalues, eigenvectors, followed by concept Cayley-Hamilton theorem and spectral theorem. Just some 3 to 4 questions from classroom workbook based on eigenvalues and eigenvectors, exactly 4 questions. After that, we can switch over to the concept Cayley-Hamilton theorem and spectral theorem. Now let us discuss question number 60. Just go through your handout. Question number 60. The product of non-zero eigenvalues of the matrix is a 5 by 5 matrix is given. They were asking product of non-zero eigenvalues of that particular matrix. Let us write the matrix at first. This is the matrix 1 0 0 1 0 1 1 0 0 1 1 0 0 1 1 0 1 0 0 1. So assume that this is matrix A. So what they were asking is the product of non-zero eigenvalues of A. Suppose instead of non-zero eigenvalues, if it is given like this, the product of eigenvalues, what could be the answer? 0. Because product of eigenvalues is a det. What is the det of this matrix? 0. Because the two rows are same. First row, last row are same. Or second row, third row, fourth row are same. When two rows are same, det becomes 0. So in that context, if the question is given like this, the product of eigenvalues of this matrix, the result is 0. But the question was a really worthwhile question. So there are some twists in this question. The product of non-zero eigenvalues. So the number of non-zero eigenvalues is nothing but rank of this matrix, right? Now, can you guess the rank of this matrix? The rank of this matrix is exactly 2. The rank of this matrix is 2 because it has only 2 distinct rows. First row is repeated twice. Second row is repeated 3 times. Therefore, its rank is 2 only. Its det value is 0. So rank cannot be 5. When you take any 4 by 4 block, either these 2 rows or these 2 rows will be repeated. So rank cannot be 4. Similarly, rank cannot be 3. But when you look at this 2 by 2 submatrix, its det is non-zero. That means its det is 0. The size of this matrix is 5 by 5. So rank cannot be 5. Next, rank cannot be 4. Because you take any 4 by 4 submatrix, det is 0. You take any 3 by 3 submatrix, det is 0. But when you look at this 2 by 2 block, its det is non-zero, therefore rank is 2. Since the rank is 2, A has 2 non-zero eigenvalues. A has 2 non-zero eigenvalues. Now, since A has 2 non-zero eigenvalues, you can easily get the trace of this matrix. What is the trace of this matrix? 5. That means 2 eigenvalues are non-zeros and remaining eigenvalues are zeros. Therefore, sum of 2 numbers is 5 means they can be 2, 3 or 6 minus 1 or 100 minus 95 like this. Therefore, let us try to find at least one of the eigenvalue. Since rank of A is 2, A has exactly 2 non-zero eigenvalues. Now, let me find out at least one of the non-zero eigenvalue. If I able to get one non-zero eigenvalue, so finding remaining non-zero eigenvalue is a simple task. Now, I use the concept eigenvector to find one of the non-zero eigenvalue. So here, let K be a non-zero eigenvalue. K be a non-zero eigenvalue with eigenvector x equal to a, b, c, d, e. Since it is a 5 by 5 matrix, eigenvector size will be 5 by 1. Now, let us apply the definition of eigenvector A into x equal to lambda into x. A is original matrix. Lambda is this value k. So therefore this is 1 triple 0 1, 0 triple 1 0, 0 triple 1 0, 0 triple 1 0, 1 triple 0 1 into x is this A B C D E equal to lambda is k into A B C D E. Now in this expression, let us try to expand first and last rows at first. So when you expand first row and last row, my results are like this: 1 into A plus 0B plus 0C plus 0D plus E equal to Ka. So when you expand first row, the result is this: A plus E equal to Ka. When you expand last row, you will get A plus E equal to Ke. So LHS part is same. Therefore, make RHS quantities equal. Therefore, Ka equal to Ke. So K is a non-zero number, cancel out this. You will get A equal to E. So replace A by E in this expression. You will get E plus E equal to Ke. So from this you will get K equal to 2. Therefore, one non-zero eigenvalue is 2. Therefore, the trace of this matrix is 5. So since its rank is 2, number of non-zero eigenvalues is 2. That means 3 eigenvalues are 0 because size is 5 by 5. Rank is 2 means 2 non-zero eigenvalues and remaining 3 eigenvalues are 0. By doing this eigenvector concept, we got fourth eigenvalue 2. Its trace is 5. So next eigenvalue will be 3. So therefore these two are non-zero eigenvalues. Therefore the product of these two non-zero eigenvalues is 2 into 3. Therefore it is 6. So this is the beautiness of eigenvector. In this question, we don't know what is the value of A, what is B, what is C, what is C, what is D. Without knowing A, B, C, D, E, we can able to get the one of the non-zero eigenvalue. Note this point. #61. Given that 1, 2 are eigenvalues of a matrix A, what are the corresponding eigenvectors? 0.6, 0.8. So A is 2 by 2 matrix with these two eigenvalues. This is eigenvector of A with respect to 1, and with respect to 2, the eigenvector is 0.8 minus 0.6. 0.8 minus 0.6. Then they were asking the element A2, 2. This is nothing but second element in the second row. Instead of giving a 2 by 2 matrix A, its eigenvalues are given and its eigenvectors are given. So they were not asking entire matrix, they were asking one particular element in the matrix. A2, 2 means second element in the second row. In our basic notation, this is given by A22. Now let us see here, lambda 1 equal to 1, lambda 2 equal to 2, x1 is this. But here some decimal values are there. If something is an eigenvector, its non-zero multiple becomes an eigenvector, right? So let us multiply this equation with 10 so that my simplification will be very easy. Now multiply this with 10. So lambda 2 equal to 8 minus 6. So assume that the matrix A is A, B, C, D. So this I need to find second element in the second row. Now therefore let us apply eigenvector definition with respect to first eigenvalue. This is A into x1 equal to lambda 1 into x1. What is matrix A? This is A, B, C, D into x1 is 6, 8 equal to lambda 1 is 1 into 6, 8. Since I want D, I expand only second row. It is not required to expand first row. D is available in the second row, expand only second row. So 6C plus 8D equal to 8, equation 1. Now apply second eigenvector, that is A into x2 equal to lambda into x2, lambda 2. So this implies ABCD into second eigenvector is 8 minus 6. Lambda 2 is 2. So expand second row, we get 8C minus 6D equal to minus 12. Now this is equation 2. Now in equation 1 we have two variables C and D. In equation D also we have two variables C and D. Now eliminate C, you get the value of D. That is required for us. This is second element in the second row. Now here this is before C, it is 6. Now before C it is 8. Now let us multiply this with 8 and this with minus 6, for example. So equation, let us multiply equation with minus 8. Minus 8 into equation 1 implies minus 48C minus 64D equal to minus 64. Let us multiply second equation with 6. 6 is multiplied with equation 2. This becomes 48C minus 36D equal to 6 into minus 12. This is minus 72. Now this implies, add these two equations, minus 48C plus 48C gets cancelled, minus 64D minus 36D minus 100D equal to minus 136. Therefore the value of D is 1.36. This is required value. So option C is right answer. Is this clear? Right. Next, we move to question number 62. What is this question? A matrix M has eigenvalues 1, 4 with the corresponding eigenvectors. Then they were asking the entire matrix. So this is similar to previous question, but in the previous question only they asked a particular element, but in this case total matrix is given in the options, right? So this can be almost same as previous question. Let us see. 2 by 2 matrix, instead of 2 by 2 matrix is given based on the options and based on the data, it is clearly understandable that M is a 2 by 2 matrix with 2 eigenvalues 1 and 4, 2 eigenvectors. Therefore what is the matrix? You can, one thing is you can get the value of any entry inside the 2 by 2 matrix, just like previous question. Just go through first option. The first element is minus 4. In the second option 9, in the third option 2, in the fourth option 3. So the first element in all the options are different. That means A11. So if you find the starting element in the matrix, you can get the answer easily, just like previous question. Okay, that is one way. So you can do like that. Let me solve this in a different way. That is by verification of options. Now what is my matrix? M is my matrix. Eigenvalues are 1, 4. What are the eigenvectors? 1, minus 1, and second one is 2, 1. So they were asking the matrix M. Now let us verify options. What is my first matrix? Minus 4, minus 8, 5, 9. I am verifying through eigenvector. So minus 4, minus 8, 5, 9. This is x1. 1 to 1 minus 1 equal to 1 into 1 minus 1. This is not equal. I am verifying this. This is verification. Now let us in this case, this is am x1 lambda 1 into x1 minus 4 into 1 minus 4 minus into 8 plus minus plus 8 equal to 1. This is wrong. Therefore, this is not an eigenvector of this matrix with respect to this eigenvalue. Therefore, option A is wrong. Now let us go for option B. Option B is this 9, 8, 5 minus 4 into 1 minus 1 equal to 1 into 1 minus 1. Expand first row, you will get 9 minus 8 equal to 1. But when you expand second row, you will get 5 plus 4 equal to minus 1. This is wrong. Therefore, even for second option, the eigenvector is not matching. Therefore, option B also wrong. Next, go through C. This is 2, 2, 1, 3 into 1 minus 1. Is it 1 minus 1? Let us see. So 2 into 1, 2, 2 into minus 1, minus 2 equal to 1. 2 minus 2 equal 1. This is also wrong. So therefore, for the first three options, the first one is not a corresponding eigenvector with respect to eigenvalue 1. Therefore, A is eliminated, B is eliminated, C is eliminated. Therefore, for this question, option D is right. C is also eliminated. D is right answer. This is one way. This is one way. Suppose if first eigenvector matches, then verify second eigenvector. Second eigenvector. So if both satisfies, then that could be right answer. That could be right answer. So, or another way is just like previous question. In the first option, first element is minus 4. Second option, first element 9. In third option, it is 2. In fourth option, it is 3. The first element in all the options is different. So you find that element just like previous question. You can get the answer easily. That is one way, and this is verification. Now we discuss question number 63. Probably this is the last question on the concept eigenvalues and eigenvectors. This is similar to previous question exactly. A matrix has eigenvalues minus 1 comma minus 2. The eigenvectors are 1 minus 1 and 1 minus 2. Then the matrix is just like previous question. Now let us try to eliminate at least one or two options just based on eigenvalues. What is option A? This is 1 1 minus 1 minus 2. Now here sum of diagonal elements, here trace is minus 1, 1 plus minus 2. But when you add these two, you are getting minus 3. Therefore, these two are not an eigenvalues of this matrix. A is eliminated. Now let us come to option B. This is 1, 2, minus 2, minus 4. Here that is 0. Because R2 equal to minus 2 into R1. One row is a constant multiple of another row. That is 0. When that is 0, at least one eigenvalue is 0. But no eigenvalues are 0. Therefore, B is also wrong answer. Suppose if you go to C, what is C? Minus 1, 0, 0, minus 2. It is a upper triangular matrix. So, eigenvalues are minus 1 and minus 2. If you go to option D, so 0, 1, minus 2, minus 3. Here also the eigenvalues are minus 1, minus 2. Therefore, option C and option D have same eigenvalues minus 1 and minus 2. Therefore, to eliminate option C and option D, there is no use with eigenvalues. Eigenvalues may not be useful to eliminate option C or option D. Therefore, but just by using eigenvalues, we have eliminated option A and B just by using eigenvalues. Because in case of option A, trace is minus 1. but in case of virtual, trace is minus 3. Trace is sum of eigenvalues, so A is eliminated. When you look at second option, trace is minus 3. When you add, you will get minus 3. But det is 2. But in this case, det is 0. Therefore, second option does not match with these two eigenvalues. Therefore, just by using eigenvalues, we have eliminated option A and option B. But when you go through option C and option D, they have eigenvalues minus 1 and minus 2. Therefore, let us apply these eigenvectors to eliminate C or D. Now let us start with the C. C is this minus 1, 0, 0 minus 2 into what is my first eigenvector? 1 minus 1 equal to eigenvalue is minus 1. So this is minus 1 into 1 minus 1. When you expand second row, you will get 2 equal to this is 1. This is also wrong. Therefore, for option C, 1 minus 1 is not an eigenvector with respect to eigenvalue minus 1. For option number C, 1 minus 1 is not an eigenvector with respect to eigenvalue minus 1. Therefore, option C also eliminated. Therefore, D is right answer. D is right answer. Not this. Eigenvalues and eigenvectors. Next, we move to the concept Cayley-Hamilton theorem. The next concept we need to discuss is Cayley-Hamilton theorem. Suppose we have a n cross n matrix A. A is my n cross n matrix. Its characteristic equation is det of A minus lambda I equal to 0. Since it is a n cross n matrix, when you define its characteristic equation, the result is a polynomial of degree n, and that result will be in this form: a0 into lambda power n plus a1 into lambda power n minus 1 plus a2 into lambda power n minus 2 plus and so on plus an equal to 0. Therefore, this is nothing but the characteristic equation of general n cross n matrix. Now, in this expression, replace lambda by a. So, a0 into a power n plus a1 into a power n minus 1 plus a2 into a power n minus 2 plus and so on. At the last constant, this is basically an into 1. For which matrix all eigenvalues are 1? Identity matrix. Of course, even for some another matrices also eigenvalues are 1, but this 1 is replaced by I. So, replace 1 by I. Therefore, this is general polynomial expression in the variable lambda. This is a polynomial expression in the matrix A. What we are doing is we are simply replacing lambda by the matrix A. Replace a corresponding eigenvalue with the corresponding matrix. Therefore, in this case, this 0 is a real number. This is a real number. But when you simplify this, you will get, oh, this is a null matrix. This is a null matrix. Therefore, what is the conclusion of Cayley-Hamilton theorem? Every square matrix satisfies its own characteristic equation. This is my general n cross n matrix. This is my characteristic equation. So, replace lambda by the matrix A. So, when you replace lambda by A, it turns to one matrix form. So, at the last constant, that constant is replaced by a constant into I, because this an is an into 1. The identity matrix has all eigenvalues equal to 1. Therefore, this last constant an is replaced by an into 1. Now, this is a number expression. This is a matrix expression. When you simplify this, you will get a matrix, because this is constant matrix power, because its degree is size. A0 into, for example, a cube, for example. A1 into a square. A2 into a plus an into I. So, when you simplify this, you will get matrix, and that matrix is null matrix. So, this 0 is real number, this O is null matrix, because all eigenvalues of null matrix are zeros. That means every square matrix satisfies its own characteristic equation. That is nothing but Cayley-Hamilton theorem. Now, let us discuss what are the basic advantages of Cayley-Hamilton theorem shortly. First, write this point. Every square matrix capital A, every square matrix capital A satisfies its own characteristic equation. Every square matrix capital A satisfies its own characteristic equation. Every square matrix capital A satisfies its own characteristic equation. Now let us discuss the basic applications of Cayley-Hamilton theorem by taking one simple 2 by 2 matrix. Suppose I start with A equal to, for example, 2, 1. For example, this is 3, 0. Now let us see, in this case, the sum of these two rows is minus 3, 3. The sum of these two rows is 3. Therefore, sum is uniform, so one eigenvalue is 3. But trace is 2. Therefore, second eigenvalue is minus 1. So, therefore, lambda 1 is 3, lambda 2 is minus 1. You can easily verify its eigenvalues. So, by taking characteristic equation or by using shortcuts to trace or uniform sum like this. So, 2 plus 1 is 3, 3 plus 0 is 3. So, one eigenvalue is 3. But to trace is 2. Already 3 is covered. So, second eigenvalue must be minus 1 because 3 plus minus 1 equal to 2 plus 0. Therefore, its eigenvalues are 3 minus 1. Therefore, its characteristic equation is lambda minus 3 into lambda plus 1 equal to 0. Therefore, this is the characteristic equation of this matrix. This implies lambda square plus lambda minus 3 lambda minus 2 lambda minus 3 equal to 0. This is my characteristic equation. Now replace lambda by a square minus 2a minus 3i, you will get null matrix. Let us verify this. Let us verify. So here let us calculate a square at first. A square equal to a into a. My a is 2130 into 2130. Therefore, this is 2 into 2 plus 1 into 3. This is 7. 2 into 1 plus 1 into 0, 2. 3 2's plus 0 is 6. This is 3. So, a square equal to this. Now, let us evaluate this. A square minus 2a minus 3i equal to a square is 7263 minus 2a. Multiply this matrix with 2. So, this is 4260 minus 3i. So, 3003. Now, let us simplify this matrix. 7 minus 4 minus 3, 0. 2 minus 2 minus 0, 0. 6 minus 6 minus 0, 0. 3 minus 0 minus 3, this is 0. Therefore, this is a null matrix. Therefore, not only for this example, it is valid for any n cross n matrix. We have verified this by taking simple 2 by 2 matrix. Right? Therefore, this is the 2 by 2 square matrix. These are my eigenvalues. This is my characteristic equation. When lambda is replaced by a, this 0 is replaced by null matrix. Therefore, a square minus 2a minus 3i equal to 0. Therefore, this square matrix satisfied its own characteristic equation. Now, my question is, if every square matrix satisfies its own characteristic equation, if every square matrix satisfies its own characteristic equation, what are the advantages we get, additional benefits? Let us see. Suppose I want to calculate a cube. I want to calculate a cube in terms of a only, in terms of a. Now here a square minus 2a minus 3i equal to 0. Here a square minus 2a minus 3i equal to null matrix. Therefore, this is a square equal to 2a plus 3i. Now let us multiply this equation with a cube. So a cube equal to 2a square plus 3a. This implies a cube equal to 2 into this a square is replaced by this quantity. So 2a plus 3i plus 3a. Therefore, this is 2 2 is 4 plus 3, 7a plus 6i. Therefore, we got the expression for a cube in terms of same matrix A. This is one advantage. Like this, you can find a power 4, a power 5, even large powers of A also. Therefore, the basic advantage is we can get the positive powers of a matrix A in terms of same matrix A. This is one advantage. Even I will discuss second advantage shortly. Meanwhile, you try to understand these points. So when you try to find its characteristic equation, when you verify, we got directly a square minus 2a minus 3a equal to null matrix. Suppose I want a cube, positive powers of a matrix A. So let us multiply this equation with a. Finally, I got a cube equal to 7a plus 6i. So therefore, I got powers of A, I got A cube in terms of same matrix A. So one basic advantage with Cayley-Hamilton theorem is we can find the positive powers of a matrix A in terms of the same matrix A itself. Right? Note all these points. Now let us see the another advantage of this Cayley-Hamilton theorem. Now here we got a square minus 2a minus 3i equal to null matrix. Now in the previous case, in this example only, det is non-zero. When det is non-zero, A inverse exists. So let us multiply this equation with A inverse. So A inverse into a square minus 2a minus 3i equal to A inverse into null matrix, null matrix. This implies A minus 2i minus 3 into A inverse equal to null matrix. This implies 3 times A inverse equal to A minus 2i. Therefore, this implies A inverse equal to 1 by 3 into A minus 2i. So, this is another advantage of Cayley-Hamilton theorem. What we got in this case? We got the inverse of a non-singular matrix A in terms of same matrix A. Basically, it is in the form 1 by det A into adjoint A. Sometimes there can be some changes with a minus sign. Suppose if this is adjoint of A, then this will be 3. Suppose minus of this is adjoint, then minus 3 is det value. Therefore, another advantage with Cayley-Hamilton theorem is we can find the inverse of a non-singular matrix A in terms of same matrix A itself. Note this point. Note, by using Cayley-Hamilton theorem, one can find, by using Cayley-Hamilton theorem, one can find, point number 1, the positive powers of a matrix A, in terms of A itself. By using Cayley-Hamilton theorem, one can find, point number 1, the positive powers of capital A in terms of A itself. The positive powers of A in terms of A itself. Point number 2, the inverse of a non-singular matrix A, in terms of A itself. The inverse of a non-singular matrix A in terms of A itself. Next concept is spectral theorem. Suppose if lambda is an eigenvalue of a matrix A, assume that lambda is an eigenvalue of a matrix A, then E of lambda is an eigenvalue of a matrix combination E of A. Let me tell you what is this E of A. This is nothing but any expression in terms of A. Any expression in terms of the matrix A, like this. So suppose lambda is an eigenvalue of a matrix A. Then E of lambda is an eigenvalue of matrix E of A. E of A means anything in terms of A. In previous sessions, we have gone through eigenvalues of A square, eigenvalues of 3A, eigenvalues of 4A, for example. So in previous sessions, we gone through eigenvalues of A power K. So eigenvalues of multiples of A, eigenvalues of this combination A plus or minus Ki. Now you can take E of A like this, E of A like this, E of A like this, or even you can combine all these expressions. Let me tell you one simple example. Suppose A is a 2 by 2 matrix. A is a 2 by 2 matrix having eigenvalues, for example, 1 minus 2. Suppose I have an expression 4 into A cube minus 3A plus 2 into A inverse. Now this is nothing but E of A. This is E of A. Suppose if I want, this is an expression in terms of A. You can see powers of A are covered, multiples of A are covered, inverse is covered. Now this is E of A. Now since A is a 2 by 2 matrix having eigenvalues 1 and minus 2, based on these two eigenvalues, I can easily get the eigenvalues of this expression in terms of A. Now just simply A is replaced by lambda. So replace A by 1. One of its eigenvalue is, replace A by 1. So 4 into 1 cube minus 3 into 1 plus 2 into 1 inverse. This is one of its eigenvalue. You will get some number. Second eigenvalue is replace A by minus 2. So 4 into minus 2 whole cube minus 3 into minus 2 plus 2 into the eigenvalue of A inverse is reciprocal, minus 1 by 2. So replace A by minus 2, you will get minus 1 by 2. Therefore, when you simplify this, you get one number. When you simplify this, you get another number. So these two are eigenvalues of this matrix. Got it? So the simple point is the basic difference between Cayley-Hamilton theorem and Spectral theorem is, in Cayley-Hamilton theorem, lambda is replaced by the matrix A, whereas in Spectral theorem, matrix is replaced by eigenvalues. This is the simple difference. So if lambda is an eigenvalue of A, then E of lambda is an eigenvalue of E of A, where E of A is any expression in terms of A. Now this is one sample example. Write this. If lambda is an eigenvalue of A, if lambda is an eigenvalue of A, then E of lambda is an eigenvalue of E of A. If lambda is an eigenvalue of A, then E of lambda is an eigenvalue of E of A. If lambda is an eigenvalue of A, then E of lambda is an eigenvalue of E of A, where E of A is any expression in terms of A, where E of A is any expression in terms of A. Note down this example. Now let me tell you what type of questions they may ask you in the exam based on Cayley-Hamilton theorem and Spectral theorem. Now let us take this example. They may give questions like this. Suppose A is a 2 by 2 matrix with eigenvalues 1 and minus 2. Then det of this is blank, or some options can be given. So this, when you simplify this, you will get a 2 by 2 matrix. Det of this matrix is product of its eigenvalues. So what are the eigenvalues of this matrix? This is one eigenvalue, this is second eigenvalue. Or they may ask you trace. If they ask you positive powers of A, then you apply Cayley-Hamilton theorem. If they ask you inverse of a matrix, then apply Cayley-Hamilton theorem. Sometimes you can apply Spectral theorem also, right? So some problems can be handled very easily by Spectral theorem. Some problems can be handled very easily by Cayley-Hamilton theorem. Okay? Right. So this is the end of this session. In the next session, we discuss classroom workbook based on Cayley-Hamilton theorem and spectral theorem. Hope you understand this complete session. Thank you so much.